go from the simulation like we just saw, remote sensing from satellites and things like weather radars, of various robots like aerial robots, walking robots, robotic boats, and then sentinels across cities that stream 24/7. So right now across the Dallas area, we measure in real time air quality, such as airborne particles from the COVID size of 0.1 of a micron up to 10 microns, and also things like CO2 and other gases, light levels, and even we detect in real time bird songs and insects. So we don't do any recording of our sounds. We're not into Big Brother watching you, but we want to be able to automatically detect bird species and things of that nature. So we can see how the environment is influencing that. For example, how is pollution having an impact on not just the human health, but also the ecosystems around us. Then it also uses a lot of wearable sensors, and I will show you some exciting examples of that. So this is like a schematic, but the next one here, we actually have a video of these different, some of these platforms in action. So in the top right, you see, well, the top three right ones was actually a demonstration in a test site in North Texas in Nacona. And we had an aerial robot, which had two types of payload on it, a hyperspectral camera, which we'll look in a bit more detail in a moment, and a thermal camera and a LiDAR, but also an air quality sensing package, the same ones that we distribute across cities. Then our walking robot also had that air quality sensing package. You can see it on the top. This is a Ghost Robotics Vision 60. And then we also have a robotic boat. So on the top, that had the air quality package and the meteorology, but beneath the boat is where most of the sensing is going on. There's about 30 sensors underneath, including a sonar giving us the depth, measuring vegetation height, the bottom of the surface type of the bottom of wherever it's sailing. And then there's a set of 4 tubes measuring many components of the water, such as crude oil, chlorophyll, dissolved organic carbon, many different ions, and so on. So those air quality sensors that I mentioned, they were all built by students. And in fact, in the middle, you can see 2 students up a pole in South Dallas. And in fact, the community invited us to place this sensor there. And it's the first freedmen's community in Dallas. And it's surrounded by many pollution sources. And quite independent of us, that community and the associated community groups use the data from our sensor to close down an illegal dump. For those in this area, you may have heard of it. It was called Shingle Mountain. So those air quality sensors stream live on the dashboard you see on the left. And so each of the different color-filled symbols is a different sensor. And if you were to click on any one of those circles there, you get a real-time feed, which with a very low latency, which is in contrast to the EPA type sensors where they only give hourly averages after about 2 hours. So we measure every few seconds and stream them immediately. And then in the bottom right, you can actually see the air quality estimated from space. And then for this playback of this video here, periodically you'll see a plume of red sweep across the plot. And that's from the California fires. So obviously they produce a lot of airborne particulates. So what I hope you're beginning to see is the different sensors on different platforms can work together. And in the top middle, what we're seeing there is actually being able to pick up a leak on the UTD campus, a valve burst from space, from 600 kilometers in orbit. So each of these different aspects you can begin to see can work together and with the goal of serving society. And last but not least, the one in the middle You see our wearable sensor package. So this system measures 113 parameters, most of them at 500 times a second. And we use this for a variety of things, but one of them, we were actually able to decode the body's response to breathing in polluted air. So we're all familiar with the idea of if we look up at a light, we have an autonomic response, our pupil dilation changes in a few milliseconds. Well, a similar thing happens, it seems, when we breathe pollution. So from just the biometric sensors, we were able to accurately reproduce how many particles were in the air that we were breathing. So that was kind of exciting. And this involved so many students, like 100+ students have been involved in these various aspects. So you heard machine learning mentioned a few times earlier. We use that extensively and have done for a long time. And so the three main areas that we draw together are observation from a variety of platforms, as we've already seen, satellites, wearable sensors, sensors on robots across cities, with our simulation, and then machine learning. Now, the part where machine learning is particularly useful is where we don't have a perfect understanding. And that's actually a lot of the situations we're dealing with, but we do have a lot of useful data. So the four main ways that we normally use the machine learning are either for the calibration of low-cost sensors. This first started out for actually really expensive sensors, satellite-borne ones, for like the European Space Agency and NASA. We found we could cross-calibrate any pair of sensors in either direction very effectively using machine learning. But then that led us to extend that for, well, how about if we can calibrate low-cost sensors effectively against our reference sensors, we can then deploy many more of them. So we're using that a lot for our air quality approach that we were just discussing. But then the creation of new data products, and I'll expand on that a little more. So that is of particular use for remote sensing and space-based products, and I'll show you an example in a few more slides. And then something else which we're really excited about is called super resolution. So you might have seen on a detective movie or a CSI type thing, where there'll be a picture of someone or the license plate of a car that you can't really see, and they'll say, well, let's enhance that, and then auto-magically they enhance it. Well, now that's actually becoming a thing. It's called super resolution. So we're doing that both in a spatial context and also for wavelength. So we can end up with a much higher resolution, spectral resolution image. And then the final area, which is of particular excitement to me, is what's called physics-based machine learning. So one example of that would be if we return to the air quality issue, we really, with air quality, the air we're breathing wherever we are right now, there's hundreds of chemicals in that air. And they're reacting with each other. And we simulate that using a set of what's called ordinary differential equations. So we can speed up the simulation of those ordinary differential equations with this physics-based machine learning. But more excitingly than the speed up is, whatever our kinetic model is describing those reactions, there's always typically going to be some missing reactions we either haven't included because we weren't aware of them, or that the rates at which they occur and their temperature dependence and so on, we don't know. So the physics-based machine learning will take the observations we have of the multiple components and can help us infer the missing terms, which is really outstanding. So let's look for a moment at the multi-scale. Why would we want to have these different scales operating simultaneously? Well, let's take a very practical example. Many of us either might have lived through or have heard about Hurricane Harvey. That was a hurricane that made landfall in the Houston area, where there was a lot of oil refineries and other chemical plants. So long before this severe weather event makes landfall, we can see it from space with the satellites. And in the meteorology too, the models will typically be using the data it has together with their models to infer the landfall. Now, why that's important is where the hurricane makes landfall will really be critical for what areas may need to be evacuated. So if very large areas end up being evacuated needlessly, then it breaks people's confidence in the forecast, and maybe next time they'll ignore them. So it's really important to have that large scale view, but then the minute the hurricane makes landfall, the hyperlocal features make a very big difference. For example, if you happen to live near the coast, what is the slope of the street that I live on? Will my house be inundated? Or as happens in Hurricane Harvey, there were entire neighborhoods that got inundated, and that water had just come through some of these oil refineries and Superfund sites and was now laden with volatile organic compounds that were now outgassing, causing severe respiratory issues. And then when the cleanup crews went in, sometimes they were unaware of what was in the water, so they didn't have the protective clothing, and then they had needless issues. And then so you can see there's a whole cascade of challenges that can really be very useful if we can have the timely, actionable insights on multiple scales. So not just where the water is, but what's in the water. So that's where the robots can be of particular use. But it's not just on a spatial scale, it's also multi-temporal scales. So, and then there's an interaction between the two and the physical environment and the social environment. So to give us an example, a concrete example of the why are we doing things on multiple scales from all these platforms, including the robots, let's just look at a very human, practical example. So this is a map of the infant mortality rate by zip code around Dallas. And so where it's green, there is 0 infant mortality, which is wonderful. But some of the areas, as you'll see, aren't in green. They are the red areas, for example. So there's a red area there just south of Dallas where actually one of our sensors was being mounted up a pole that we saw in the earlier picture, where there are substantial amounts of infant mortality. And that goes hand in hand with a whole set of other health outcomes like cancer, stroke, diabetes. So the physical environment is impacting the human and social environment. And so having actionable insights can make a big difference on the everyday level. So let me just give you 2 practical examples. The leading cause of absenteeism from schools is asthma. The leading cause of asthma is inhaling, trigger for asthma is inhaling polluted air while strenuously exercising. So now if you're a school coach and you have like PE or practice of various kinds, but you have kids with asthma in your class, you can actually check the real-time data to decide should practice be outside or inside. But then it doesn't stop there, because an asthma event can be very unpleasant, and it can end up with the person being in the ER, which is really not nice. But then in addition, because they're absent, they miss class, it affects their learning outcomes, but also the school doesn't get paid because they get paid by attendance. So if we can have these timely alerts, then we can preclude this, have a sustainable solution, and it's like a win-win. But there's also aspects we may not have thought about. It's becoming increasingly apparent that the air quality doesn't just impact our physical performance, but it also impacts our cognitive performance. And so we each like to feel really sharp, and we don't think that the air quality we're breathing actually is making a difference, but it does. And so the popular press will say something like dirty air makes you dumb, and the scientific literature will say something like the impact of exposure to air pollution on cognitive performance. But they're essentially saying the same thing. So that air quality package that we mentioned earlier was on each of our robots. And the reason that's there is not only is that useful for, say, in some bio-release event, and hopefully not a terrorist one, but it's also useful for the air quality. So these tiny particles, so the one that there's a very much blown up picture of there on the left is of a 0.1 micron particle. So this is actually about the COVID size. So these particles, they're often termed ultrafine particles, are like Trojan horses. When we breathe air with these particles in, they can get deep down in our lungs. Then that can, actually the particles can cross the barrier into the bloodstream, and then from the blood actually into the brain. So then it causes inflammation, and then a host of other things result from that. So normally this small size fraction is never measured, but we've found that we can use these low-cost sensors to do so, help infer them from space and from the various robotic platforms. So hence this live map that I mentioned. And overlaid on here, we also have the weather radar and the wind speeds. So the arrows that you can see is how the wind is flowing. And of course, whether there's a fire or any other kind of plume, that will affect the concentration. So the various platforms that our sensors hitch a ride on, you see some examples here. They can be a satellite, a little mini drone, which is just an inch or two across, a much larger one that you see in the middle, which is designed for movie making. So the movie Venom, for example, used this exact same robot to do a lot of the filming. Then the walking robots and the robotic boats and so on. So in most of these cases, the robot is really the ride for our sensors. So each sensor will need power and communication, and then it will need a platform to be on, whether that's a robot, a satellite, a street level sensor, or even a person in the sense of the wearable ones. And so one way that we can use machine learning very effectively is by doing what we call software-defined sensors. So one example of this that we're using in the air quality case, and then I'll show you an example for the remote sensing case next, is at the top we have a low-cost sensor that can measure air quality that's being distributed across schools and cities and so on at the moment, in fact. And then we can calibrate that against a high-end reference sensor. So that means because they're much cheaper, we can readily distribute them at scale. And when they're solar powered, that's very helpful because we don't need a power source there. But then we also use communication, something called LoRaWAN. That's low is for long, Ra is for range, and then the WAN is wide area network. So this can communicate over quite large distances, depending on how many buildings and what obstructions there are, up to a few miles. So that helps us keep our costs down because we can have a gateway connected to the network, and then these low-cost sensors can communicate back to those gateways. So we use the machine learning to learn how to calibrate the low-cost sensor, and we can actually often do a variety of things. So you can imagine these software-defined sensors could also have an onboard app store that as we figure out how to do more things with them, we can update their capabilities. A similar thing can be done for the remote sensing. So the reason we had an aerial robot and a robotic boat was actually very specific. The aerial robot had a hyperspectral camera. So that little colorful thing you see on the top left is actually a stack of images. So when we take a picture, say with our mobile phone, we have a red image, a green image, and a blue image that's combined to give us our color picture. But with this camera, instead of having 3 images, we actually have over 490. So for every pixel, we have an entire spectrum. And that spectrum tells us about, in this case, say, what's in the water. And then the boat underneath the flying aerial robot is actually measuring what's in the water. So the aerial robot and the robotic boat are on the same network. They communicate. The boat streams the data to the aerial robot, which has the hyperspectral camera, and then we have real-time machine learning that learns the mapping from one to the other. Now, previously, when I was at NASA, to gather the appropriate data could sometimes take more than a decade. I will revisit that in a moment. But here, in 15 minutes, we could gather as much data, just in terms of the volume, as was previously done in more than a decade for the space-based instruments. So again, we can use the machine learning to learn the mapping from the remote signal to the in situ one, giving us our software-defined sensor. And again, we can have an associated app store and a whole variety of products, such as, for example, different components of the water. So our sentinels then are some software-defined sensor on board a platform, which could be a robot, a street side location, or a person with the wearable sensors that can have its own app store. And then multiple sentinels could be combined together for our cyber physical observatory. And that also could have an app store for how to combine these various information streams simultaneously. So prior to doing it in this way, the way it would be done is illustrated by the schematic on the left. So our remote sensing platform, say our satellite, would stream the data to a ground station. So the latency, the delay associated with that will depend exactly on where the satellite is and what ground stations it can see, but could be of the order of a couple of hours before the data ends up in a data center. Then to create our various data products, we would separately have to collect the ground truth, say from an ocean-going scientific cruise, and then the data would be combined typically in a more manual way by, say, a scientist or an engineer bringing them together. So the whole time to take our product development could easily be a decade or more. But the paradigm on the right that we're using in here, we actually do it in real time. So the boat streams the ground truth to the aerial vehicle has the remote sensing and the onboard machine learning. It learns the mapping, does the machine learning, creates our product, which we can then in real time while it's flying. So that's basically what was going on with this case here. So for this pond, we did a survey for in North Texas. Here I've shown a map. The background colors show the crude oil estimate from the remote sensing, and the overlaid color-filled squares was the sort of ground truth that the boat measured. And what you'll notice is the colors correspond to the amount. So all of this was very low amounts of oil. So you can see it's around 26 parts per billion. So for every billion water molecules, there was only like 26 oil ones. But you will notice that part of the pond has higher values where the reds are. And that's because that bit of the pond is isolated. So in the bottom right, you'll see there's the creek runs through there. And then in the top right, it exits over a little dam. And so the larger area of the pond has far more water changes than the more isolated area in the top right. And you see quite a gradient across the inlet. So the system I just described could collect the data, learn the mapping rapidly in real time. So it may never have seen this location before. It may never have encountered those components, but the robotic team goes out, acquires the data it needs to then provide the large area map. So let's do a bit of a deeper dive. Let's take something that is more in our everyday encountering. So if we go out, say, of our house or walk in the park and we see the grass, if it's been raining a lot, typically that will be nice and green. But if there's been a drought or it's been dry for a while, it will not look so green. It'll get more yellow or brown. So what causes that green appearance is the chlorophyll, which is the molecule you see on the left. And that chlorophyll has characteristic absorbances based on the strength of the various bonds that are in that molecule that can absorb the light. So in the middle plot here, you see two different spectra of two different types of chlorophyll. And what they both have in common is in the green part of the spectrum, they are not absorbing. They're absorbing the reds and the blues. So as a result, the leaves of the grass will look green because the green hasn't been absorbed, but the red and blue has. So what we are doing essentially with our aerial robot is it has the hyperspectral camera on, providing us like a stack of images like you can see here. So vertically in this stack is the wavelength of each pixel. And you can see that the spectral features can be very different at different wavelengths. So the area I've highlighted in the stack with this dotted red area is where we released an inert dye that is used for water tracking as a test. And you can see that in the top left image as these red plumes. And then on the stack of images, you can see that same area as this very distinct spectral signature. So that's looking down at the water, but we also have a sensor looking up to see what light is coming in from the sun at very fine resolution. So this is an example spectra that we obtain on the top of the robot looking up towards the sun. So we know the light coming in, we know the light coming back up, and then we also know what's in the water, and we use the machine learning to map the two. But as the aerial robot flies, it can be jiggling a little. If there's a gust, the orientation can change. So another thing that's happening in real time, which normally has happened after the robot would land, is called georectification. So in real time, we use the orientation of our robot, which we measure with IMUs, inertial motion units, to know exactly which direction we are looking at. And so that then is turned into what ground location is the robot currently looking at. So for every pixel, we can end up with a latitude and longitude that is actually being observed. So that's actually quite a time-consuming process. So instead of waiting till we land, we do that in real time. So then once we have that information, we know for every single location what the remote signature is, and also what the ground truth would be, say from the robotic boat. We combine them with our machine learning, and that lets us create our wide area maps. So yeah, so this is a different molecule here. Instead of chlorophyll, this is the rhodamine dye that was used, and it's used as a hydrological tracer to track water flow. So if you are wanting to do a similar thing with your robots, the inputs I've shown in green are the various things that are being measured by the robot. In this case, they're the intensity at different wavelengths of light from our hyperspectral camera. And the outputs, the orange column, is the ground truth that our robotic boat is measuring. So we use the machine learning to map these inputs to the outputs, and we don't just try one approach, we try a whole set of learners, and then we combine them in what's called a super learner. We can, yes, so this is just a schematic of that process. And that results in us being able to produce in real time maps like this. So that's really exciting because you could quickly survey an area that could be contaminated you haven't seen before, that could then be a heads up for, say, whichever teams may be going in for the cleanup, if we go back to the Hurricane Harvey example. Or you could go one step further, and the robots could also be part of the cleanup. So as in the case of harmful algal blooms and oil spills and so on. So, and then the multi-use, we don't we wouldn't just use this in one context, say for the contaminated environments we've been talking about, or the air quality across cities, and more people are moving towards cities. But those same sensors can be used to look at things like breath analysis. So for example, we've all just lived through COVID, and it turns out that within an hour of us, if any of us are infected with a virus, typically the composition of our breath changes. So looking at those metabolites can be of great use as either for detecting the virus, early onset of various health conditions, or even things like diabetes. So instead of having the pinprick to see your blood sugar from your breath composition, you could actually infer your blood sugar levels. So that's another very exciting area. So, yes, sir.
So we're like running behind schedule right now.
Okay.
And like more speakers, can you like wrap this up for us?
Yes, sir. It is wrapping up. Well, okay, I can stop there. There you go.
Okay, thank you, Professor David Larry. We don't have much time for questions right now, so we'll collect your questions and then forward them to Professor David Larry later. Thank you again for presenting, Professor. Thank you.
Okay, give me 1 second. I'm going to introduce our next speaker. Okay, so today I would like to introduce Mr. Subhajoy Dutta, the Managing Director of S&M Engineering LLC. Mr. Dutta has double post-graduation in mechanical engineering and petroleum geological engineering. He has worked for 20 years as a senior engineer at US EPA in Washington, D.C. He is now associated with EPAs of multiple countries. Today, he will be talking about how to capture and reduce carbon dioxide emissions in the environment. Everyone, welcome Mr. Dutta.
Okay, should I open my presentation?
Yeah, you can open your presentation.
Okay, okay, let me see. Okay, can you all see it? And good morning to everybody.
Yes, we can see it.
Thank you. I really enjoyed the presentation by Dr. David Larry. It really leads to some of the thoughts that I have in this particular presentation, that you can probably see the application of such use. And mainly, I want to cover today carbon capture, on the carbon capture theme, what you could think of, innovate, and go forward with. Sensing is definitely important, as Kevin Larry pointed out. And without monitoring and sensing, you cannot really go forward on anything. So today, I'd provide some climate change issues and impacts, which is the broad picture, why we need to develop all these tools and techniques, and some general observations, some recent impacts. And I looked at analyzing those from the perspective of damage done, carbon lost, and how much carbon emitted, and what we could do, and those sort of things. Also, I myself took exceptions to some of the glacier splits and events that happened. And it threatened some of the people that I know, some of the schools that are sitting in a vulnerable area. So I went to a glacier. I'll show you the study there, the Himalayan glacier, and building climate resilience, which is, how you protect and to build climate protection. There's one part of the kind of situation. The other, lowering the global temperature rise, what sort of things could be done. And it's all working together. That's the main part of it. I mean, we all have to work together to achieve this. So I'll go through some of the slides and then let's see. In 20 minutes, I hope I can finish, but I want to have a few questions and reactions from all of you. That's very important so that, I understand that you've got the gist of it. Here is a California forest, which is a robust carbon capture device. If you can think of this forest, for a second, go inside it, see what we look at. It's full of oxygen. You walk through it, you get rejuvenated. These trees are capturing carbon dioxide, converting into oxygen. And it's a process through hundreds of acres, thousands of acres there. And to protect those, to prevent anything from happening, I really refer to some of the techniques David Larry indicated, and that will be very useful, and some thoughts. It should give you some thoughts of how to do those things. One sudden lightning during the fall days or dry days of late spring, this lightning caused fires, such a tremendous fire in the California wildfire last year. It happened, and a massive carbon emission that takes place. Now, you talk about carbon capture. Carbon capture is also how much carbon you do not release, how much carbon dioxide you prevent from releasing. This is a massive event, and you are releasing tons and tons, millions of tons of carbon. Of course, this is a natural event, but sometimes there's artificial, people light fires, and that also happens. Now, if you had instrumentations, if you had real-time monitoring of any simple infrared sensors also can tell you if there's sudden jump or sudden change in temperature, etc. So, and if that could be reported, and the robotic system that is available today, and some of it you have seen in the previous presentation, that could monitor 24/7 such things and send a signal, send a notification to people, alert them. If it is kind of put under control within a couple hours or even in 2-3 hours, you can control a huge destruction, a huge emission of carbon. And that's one thing I would like you all to look at, think about, and see what could be done. And you can put it in your present what is the challenge, the global environmental challenge. I think that would definitely make a way for newer solutions. So here, so the glacier breaks in Uttarakhand, India, near the Himalayan hills. It led to flooding and devastated a village named Rishiganga, just carried it away. And all these things happened because this glacier was slowly melting. It's climate change, of course, but nobody noticed. That's the tragedy, and that's where I'm trying to focus on one aspect: is climate resiliency, building climate, impact, protecting the people, protecting vegetation, protecting lives, wildlife, animals, and all the creatures. And what's happening there is, you've got so many different losses, and your total loss in carbon balance, if you look at this, I just listed a few. This particular event, many trees were taken away due to landslides and floods. People rehabilitated to a new area, and they cleared trees and have the rehabilitation, their homes, and a lot of transportation of heavy equipment usage, construction, as incremental emission. So, think of this as an area where carbon capture could be achieved and disaster minimized. Those are things that I would like you to start thinking as you build your robot for the competition or further going forward. If we check on the statuses of these vulnerable glaciers, dams, and other areas, and we try to build protective measures, that will really affect both ways. It will prevent all these destructions. At the same time, we have really kind of preserved the carbon that is there to do the job, keep the oxygen flowing and carbon dioxide capture. And those are really a carbon dioxide capturing machines. You can say each tree is a huge machine. It can help protect the loss of existing which is trees, and that's what I meant, and reduce additional carbon emission in the rehabilitation process. So these thoughts, when I looked at the Rishiganga incident, I started thinking this, and these thoughts led me to go to the Khatling Glacier in Uttarakhand last April. And I looked at what can be done. I looked at the flow of water. I looked at the melting of glacier in that particular season. So we'll cover that study briefly as I go through. Now, this initiative, the major findings by European Commission and NASA on tracking greenhouse gas emissions, I studied that quite thoroughly before I went into writing a book I wrote on this environmental technologies, treatment technologies. So human activities are increasingly adding huge amount of greenhouse gases, and this is causing this global warming. It is just for a validation that yes, global warming is taking place, we have to do something. What I wanted to mention is not only European Commission, it's also NASA. Many other agencies have shown some of the changes, some of the things that are happening if you compare 100 years ago, 150 years ago. So they're not due to more active sun. I'm just trying to validate to you, yes, it is a problem, it is a big problem. And I myself have to convince myself after reading lots of literature, not now, about 2 years ago, and just to kind of focus on this and then include some of those in the technologies that we need to focus on this when we are using the environmental technologies. And that's kind of drove me in this direction. Now, as I said, it's not the more active sun, because that would have warmed the temperatures in all layers of the atmosphere. And instead, it was observed that the cooling in the upper atmosphere is and warming at the surface in the lower parts of the atmosphere. So upper atmosphere is really not warming, because the trend now, if you see the NASA chart here, which is solar irradiance versus temperature from 1880 to 2020. We got this data from NASA, and it's an 11-year average. So you see, this is really an average temperature rise, and this is the solar irradiation or irradiance, and it's, what's 1 meter squared. And you can see from up to 1960, they were almost parallel. They were lagging each other a little bit, but they were almost parallel to the solar irradiance. Your temperature rise, it's also the temperature lowering trend, like the temperature fell, below like minus 0.2 degrees, here. So it came down in the lower Earth temperature. If we could get that here, that will be phenomenal. That's what I would like to see. And that's what everybody wants to see. What can we do? And this is again, from it all started from 1960 onward. And in 1960, you see the solar irradiance was pretty high, it's 1362 point something right here. But the lower Earth temperature did not rise much because there was a inherent natural condition that prevented such things. And but later, although the industrial revolutions came in and we changed, we had cars, trucks, and aircrafts and various things that causes emission in the industries. And so it's going up and up and up. And now any sort of a disaster or anything causes more emissions, like your fire, glacier split, etc. So looking at that, we are looking into two aspects. One is how to reverse this trend. And many of these gases, of course, are involved as a greenhouse gas. And this is carbon dioxide, methane, nitrous oxide, fluorinated gases. Each one of those are highly potential. Of course, methane is about 30 times more potential than carbon dioxide, but we have ways to capture carbon dioxide and we have ways to use methane. So people won't release methane or make all attempts to capture methane because it's really energy, it gives us ready energy. So people like that. Whereas carbon dioxide, the trees capture it and people don't even know if they're emitting some, and they don't have a specific effort. They're making now in the industry, of course, but that's what the focus of this is, capturing carbon in this particular topic. Nitrous oxide, fluorinated gases, these are also there. But the disasters, you can think of floods, landslides, mudslides, forest fires, drought, and evolving viral outbreaks. These evolving viral outbreaks is, I saw a National Geographic, I think, documentary 6 months ago or so, where they were exploring areas where the glacier melted and millions of year old rocks got exposed. And they found some viruses that are so dangerous that if it comes out, if there's an outbreak, there's nothing that we can attack people from. And if those sort of situation happens, imagine what will happen to this world. So we need to do our best to keep the temperature down, the lower temperature at a reversal, and prevent such things from happening. Anyway, so each one of those are highly disastrous. So it's causing loss of lives, damage of properties, etc. And also to cope with the climate change, as I said, there's two steps. One is to build climate resiliency, so people don't get as much damage and the lives are not lost as much. And how to get that built? Some of the ways is to innovate and notify people in time, and those use monitors, sensors, etc. Also pursuing remedial steps involving climate reversal, and that's something you are working on and you should be working on. This is the study that I did in April. Went to Uttarakhand, and the car doesn't go probably about 30 kilometers or 20 kilometers short of that glacier. Then I had to do trekking and pretty steep slopes, and it was challenging, but it was really very inspirational because you see the glacier far off and you say, no, I have to get there, I have to get there. And to see how much, what is the flow. In April, there was no rain. The monsoon starts in June in India. So in April, no rain. So any water that you see in the streams or creeks is from the glacier. So when we went further down, here is the river called Vilangana River that's coming right from the glacier from the top. And I can show you why that is. This is, by the way, it's not any rope line or anything. I didn't rope up there. I was down below. Here is the Vilangana River coming this way, and those two meets here, and it goes down. And I was standing about, this glacier is about 11,800 feet. We are at about 9,000 something down there. And this is how the flow is. You can see it's a huge amount of flow for April. And but I saw a little stream that was coming from here and joining, that was coming through, the melted glacier from the bottom and probably made their way through a spring. And this water quality is just unimaginably good, because I checked the TDS values, the total dissolved solid values from the Kansali, the village that I was concerned about from there. This is about 110 kilometers or so, the road, you can go. And the TDS, it's amazing how it was getting improved and improved and improved as we go up. And so you can see that the glacial water is really pure. It's just, I cannot explain to you. You guys have to explore it sometime and you will learn, it's just amazing. And so this water was the best of all the sampling I did along the way. But this water from this river, because it was coming through all the rocks and kind of a little bit of cutting sands while coming down, so that had a little higher, like we had about 13 parts per million here to spring and the total dissolved solid. And here the dissolved solids were about 27. But I have all those numbers, I looked at and made a comparison, made a sort of finding. So our study covers all that thing. Now, but if you're interested in the study, contact me and I'll provide you more details. Carbon capture and countermeasure, it's an initiative that, your FGC completion, you have 6 project sectors. I'm coming to your project sectors because this is what is important to you at this time. And energy, agriculture, urban systems, building, transport, industry. Now, I specialize in waste management and some agriculture, not too much, and land use, of course. And energy also, I had my first degree was in energy mechanical engineering. Yes. So anyway, so I know a little bit about energy and quite a bit about waste management, etc. So the above categories, you can identify the potentials for emission in any sector, in any industry, any process. You can identify the potentials of emissions by breaking down the process. You have to break down the process from the beginning, middle, to the end, and after end, those. And that's what I've really drawn a parallel here. This recent book that I authored very recently in September 2021, a little less than a year ago. Waste remediation steps. And that was amazing when I went to climate change issues. Of course, I broke it out before as I was to work on the waste management and treatment. But I found that if you look at every steps, like staging, initial staging, site preparation, pre-treatment, treatment, post-treatment, monitoring, and closure. So each of the steps, you have potential areas for emission. And, looking at those, you can figure out, you can have ideas that how to prevent them, how to detect them. That's another thing. Some people do not know that they're emitting methane or carbon dioxide, carbon monoxide, etc. The VOCs, the volatile organic compounds. I heard David Leary mentioned about that a couple of times. And that's the thing that you measure, it's a total. It's not just carbon chloride and various, trichloroethylene. These are all VOCs, and some of them are carcinogenic, some of them are not. It's a huge, group of chemicals that are emitted during treatment, etc., or industrial process. And so, there are other greenhouse gases that you have to look at. These were identified for each of the technologies. So I've given the ISBN number. If you can find it in the library or somewhere, take a look. And, from MIT, Professor John Leonhardt went through this whole book and wrote it forward. And I think he gave some valuable information as to how this can be used in the future. And I would like to, like you all to look at it, the climate change issues, the remote sensing technologies. What David Larry mentioned, I totally agree with such an innovation. It's wonderful to go forward with this hyperspectral imagery and things. So I have a chapter on that, and COVID-19 related waste management. Well, medical waste have incinerators, and that's where you see the emissions, how to control them. Wood scrubbers, yes, but still there will be leaks. So anyway, go forward with showing you potential areas of emission in one process only. This is solidification stabilization process. And you start with excavation. You have a waste. Somebody tells you, let's say a refinery gives you a contract to clean up one site. And then you go there, you excavate. When you excavate, huge thing happens. All those benzene, toluene, xylene, all kinds of higher carbons that are more vaporous or volatiles will kind of evaporate, and then you have to have capture and treatment of that. Similarly, mixing, obvious treatment. So in this chart, you'll see even after you stabilize it, there could be some emissions, and that's what you have to monitor. And I am really happy to have seen some of the instrumentation and robotic measurement that previous presentation had. So it is very, very kind of in line with this presentation. Very good, I appreciate it. So residuals the same. Then you have in situ processes, mixing, again, stabilized, and residuals. Residuals may have a lot of emissions. So anyway, you have to look at those. And then this is something that in a very simple sense, I thought, how you can, capture emission in a simple processes, very ground level thinking, where you have, people, I see that all the time, believe me, all the time in India, even here, sometimes I see people take their, trash, etc., yard waste, and just burn them for a, put them in the kind of a fire, outside fire, and let it burn like that. Well, a little bit is okay, but when you have acres and acre dry leaves, and if you burn them, and the emission that goes out is really bad. You are emitting a lot of carbons. Let us not do that. You can do a simple kind of a, let's say, composting, but it's a biomethanation, we call it. So you can use methanogenic bacteria, put the hydrogen and carbon dioxide in there, which is going, after you burn those or smoke them, and then generate methane. And methane can be used for many domestic uses. You can do the generators and the heating, for many purposes methane can be used. And you can monitor if there's any leak. That's very important thing to do. So this is something I thought about, and I think I mentioned to your Dallas group that this is one thing that you can do to prevent the carbon from being emitted by simple things that people do without knowing. Educate people and go to villages, rural areas. They need to be educated about this. So think about that. Now, considering your categories again, I have some of the examples that UNESCO had a document that I looked at during, earlier during my study on various climate change issues, and how to educate people, how to educate school children about this thing. Agriculture, gardening, design and maintain school gardens, compost, plant trees. And planting trees is one great thing that you guys can do. And every kind of World Environment Day or something like that, we do World Water Day all the time in India, China, Philippines. I have a organization, Rivers in the World Foundation, and I have found it also. 4 5 of us we founded that organization, and we do a lot of things on this environment. So you can do such things which will be very useful, and it will capture a lot of carbon for you. So also interview local farmers and learn how climate change is affecting them and identify issues from there. So that's another thing you can do. Your mass communication and other majors get involved, and this is one way to get them involved. Industry including waste management, and that's something I just mentioned to you. Look into your innovation in household waste management that minimize emissions, and one of this is yard waste, as I showed you before. Industry practices that are of concern and look for innovations. Now, industry practices, that is something that you have to look into industries that are nearby your locality, your community, and make some effort and have some visible changes, and so that people know that yes, this is great, this innovations work, or identify, tell them. Urban systems, interview local government officials about their actions to address climate change. So you can arrange that, and it's like a lot of new systems are coming up to prevent this damages, the carbon emissions, the greenhouse gas emissions. New building design, for example, and there is a thing about building, which is the next one I will show. Plan community environmental awareness program, which is one that we do every year on World Water Day. This is being done in UP, India, in Gokul, and they're collecting all the trash and other things lying near the river. If you don't do anything, they go into the river and just pollute the river. At the same time, you have some people collect it and burn it. That's another issue there. So building.
Hello. We are kind of running out of time right now, so I was just wondering if you could please wrap it up quickly. Sorry.
Yes.
Can you just quickly go over like some highlights or something?
Yes.
Before...
I have one more slide. That's it.
Oh, okay. Yeah. Thank you so much.
Yeah. Just one more slide.
Yeah.
Thank
sorry
you
for like all the delays and all.
Yes, I understand. So buildings, check flooding and other climate change issues that are affecting your community. Identify waste burning, as I said, that one in the schoolyard. Energy, look into energy efficiency of your home or school, or suggest changes where identified, wherever you identify to improve efficiency. And another simple thing you can do, not simple, but you are talented guys, you can do statistics on energy usage. It suggests changes to improve energy usage. Transport, use bikes, carpooling, metro, public transportation, examine the health risk of air pollution in your community. So those are some of the things that you can think about in your new deal. Okay. I just wanted to show you this picture from the Chambal River. I went there. It's a nature's paradise. If you get an opportunity, go there. You will see what nature is doing, how nature is keeping. And Chambal River is a very clean river as compared to the Jamuna River, which is coming from the north side, and they confluence right there, a little bit ahead to this side, the Jamuna River. And it is really a miraculous place and such a beautiful creation of nature. If you get such opportunities, go there. That's and I think that's all I have today. Any questions, you can send it to me.
Yeah, if you guys want to, you guys can actually send questions to him in the chat. Thank you so much for giving us this lecture. Thank you. And I think we're going to continue on with our drawings. So yeah,
Okay.
thank
you
you
very much.
so much.
Yeah, bye.
Okay.
So,
Okay, hello. So we're now going to have the drawing. Everyone in the session currently will be entered to the drawing, and here am I. I'm going to be sharing the screen. If you have won the drawing, please DM me on the Zoom chat with your email and your contact information so I can forward the gift card, which is a $50 Rev gift card. And we'll do the spin now.
So we have a winner. We have Kareem Virani. So so you guys get a
$50 Rev gift card. So can you please DM me on Zoom that you will your contact information and basically your email. Thank you so much and congratulations. And next up, we're going to have Team 118 Robonauts. Team 118, the Robonauts, is a district-wide high school first robotics competition team from Clear Creek Independent School District in League City, Texas. The team is made of 60 students from 6 different high schools, grades 9 through 12. The team has the privilege of working alongside NASA JSC engineers as their mentor. The mission of Team 118 is the Robonauts is to educate their student in the field of engineering, engage in the community in a field of engineering and STEM education, field a competitive team, and grow the Robonauts family. Today, they will be talking about their design process and climb overview. Welcome, Robonauts.
Hello, everyone. Welcome to the Robonauts design process and presentation on our 2022 Robot Horizon and a special segment on this year's climb.
Hello, I'm David.
Oh, I'm Sumi.
I'm Marcus.
I'm Jackie.
And I'm Ethan. I'm a NASA engineer at JSC, and I'm one of their mentors.
So this first step in our design process is the robot can and robot will list. So right after kickoff, we have a full team meeting and students are encouraged to pitch in ideas on anything the robot can do. This doesn't necessarily mean things that the robot will do, but it's just to get an idea of how the game may be played. This list is kind of like a series of meetings we had the weekend after kickoff. So in the third column, you can see at 6 p.m. on Saturday, we start to narrow down what our robot is going to look like. So the dashes mark things that we weren't completely ruling out yet, and the X's mark things that we definitely wanted to go forward with. So you see things like hanging on the traversal rung and picking up cargo from the ground for things that we definitely wanted to include in our design process. Going further to the right, you see our fully narrowed down list. And this was after many team discussions on how we want our robot to work. And so this was our fully narrowed down list. And then you could see we split off into subsystems such as base, hanging, intake, and shooter. And this is a critical step in our design process because we were able to all work towards a clear goal that we all agreed on.
So right after the robot can and will list is prototyping phase. And so each subsystem goes into the prototyping phase trying to figure out what is the best way to do the intended tasks and what the with the help of our water jet, we make quick work of all the prototyping. So all the sheet metal and plywood you see on these pictures are actually cut on a water jet. It's a huge time saver. So on the left, you can see that Climb is prototyping that their second claw, and they're seeing if it fits. And in the middle, you can see Shooter prototyping and testing on their wood prototype. So we do testing on like the wheel speed and hood angle to see what the best angle is to shoot from each distance. And that data is very important to us. And on the right is intake prototyping on some different types of rollers, such as Velcro, to see what the best way is to intake the cargo in this game.
So after about a week of prototyping, we usually ask each team member to come up with a drawing of what they think the robot would look like. So they're just rough sketches, what we call crayon CAD. So we just put pencil to paper. And then also at the end of week one, we usually have this year we came up with 2 different CAD models, one for each of the different climb mechanisms that we'll talk about later. And then this is the final like geometry of the robot that we decided on as a team on our Saturday night. So this is a very rough CAD model, but it really shows the team what the robot at the end will look like and how each subsystem fits together. And then so after going over our crayon CAD, we go much deeper into CAD in our software Creo. And this is where each subsystem actively puts in every single little hole, every single rivet. And then everything we do is design in CAD. This way we can greatly visualize how our robot will look. And since during our manufacturing process, all the parts are cut on our water jet again. So each part is designed in CAD and then cut on the water jet. And after actually each subsystem is designed, we do a design review just to knock out the kinks, make sure each subsystem works with the other subsystems. And yeah.
So this is the silver robot, and it's the first robot that we build and also our practice robot. It's built sometime at the beginning of week 3, and it's made to serve as a prototyping robot and also a way to get everything together without having to worry about intricacies like lightning patterns and ISOGrid. So this robot is over the weight limit, but it helps software and drivers get some practice in while we're still refining stuff for our final gold robot.
This is our 2022 robot Verizon. We will break down each subsystem, starting with our intake and then moving on to our shooter and then our base and then ending with our climb mechanism.
So here's our intake mechanism. From the preliminary crayon CAD, we decided that the intake would have to be long and have these long box tube arms so it could stow above the shooter. So that kind of gave us a feel for what the geometry of the intake would look like. And then we did a lot of testing with different roller positions and different roller materials. The second roller actually moves up and down to maintain contact on the cargo as it's pulled into the shooter. And it has larger rollers towards the outside and smaller towards the inside to kind of funnel the balls in. And this material is actually like a foam mat. We tried rubber and we tried some surgical tubing, like standard intake materials, but we decided that these were really nice because of the compression and the grip they had on this specific type of cargo. And then for the speed, since we knew this was going to be a swerve drive year, we wanted to be moving really fast and be able to intake and cycle balls through our robot pretty quickly. So as a general rule of thumb, we start with 2 times the linear speed of the robot. And then we ended up having to slow it down a little bit after that due to some issues that came up throughout the year. So a couple of those were the ball slipping on the rollers and not getting over the bumper. So we slowed it down, added more torque, and that seemed to fix that. We also wanted to quickly intake balls along the side of a wall. So we ended up adding little rollers out on the end to slide down walls and intake those more quickly. And then a third problem that we ran into was intaking 2 balls at the same time. And what we did for that is to kind of mix up the order of the rollers on the trailing roller. And so one would go in first before the other. So that's kind of how we navigated around those issues to come up with our final design.
So this is our Verizon Shooter. And so this shooter has a independent moving turret, hood, and so the hood moves on a rack and pinion mechanism powered by a Neo 550, and it also has a potentiometer for a tracking. The top hood wheel is powered by a Falcon, so we can adjust the top spin. So the turret itself, as you can see, is in the middle picture. It is a stack up of water jetted sheet aluminum with a Kadon KA110 XPO bearing with a 11-inch ID. So everything glides or rides on top of that one bearing. And as you can see, on the right side, the bigger stack is the turret, and the left little bit is attached to the chassis. So there is no other contact other than that tiny bearing right there. The bottom plate is a gear where the Neo powers the entire turret to move around, also with potentiometers tracking. So the flywheel is actually made from a huge billet aluminum CNC machine out to basically hollow. And we also have a feeder and a kicker wheel. The feeder kind of indexes the wheel all the way up to the kicker wheel, and the kicker wheel is kind of acts like a trigger, allowing the ball to get fed into the main hood and the flywheel and hood wheel. So yeah, that's how our shooter works.
So moving on to our base, on the far right, you can see a picture of our chassis. It's made entirely out of aluminum 090 sheet metal, and there are custom rivet holes along the frame. And towards the front, there are intake saddles that the full width intake rested on. So on our robot wheel list, the third or fourth thing was having Swerve drive. So we knew Swerve drive was something we were prioritizing. So this year we ran Swerve drive specialties Mark IV modules. So at the top you can see them, and we ran with an L3 gearing originally, but due to the weight of our robot, we were never getting to top speed, and under defense it was hard to get enough acceleration to move away. So we went down to an L1 gearing, and it helped a lot. Right now the robot moves at around 13 or 14 feet per second. On the bottom left, you can see a photo of our Swerve drive testbed. This was a crucial part of integrating software and base. Software basically had a testbed already made to run programs and get the code ready before we had the chassis ready. And then there's also a photo of how we mounted the Swerve modules to the frame. Mark IV modules come with 8 bolts on the plates already, and those were bolted down into the frame using floating nut plates. And there was a custom plate made of aluminum 090 underneath, and that was riveted into the frame. And then there were nut plates underneath the frame, and then the bolts from the Swerve module went into the nut plates.
So I'll talk a little bit more in depth about our climber and the development process that we went through to build it during the season. I'll go through the steps that the others have talked about as we do in every subsystem, but specifically on the climber. So those steps are to communicate concepts, like in the brainstorming phase, prototype it, CAD what we think the final robot will be, build it, solve problems when it doesn't work, and then iterate throughout the competition season. So the first step in any engineering process kind of is the brainstorming phase, but really the most important thing here is that you communicate effectively with your team. So detailed sketches here are really king. That's how you show your ideas and how they fit into the architecture of the robot, and you describe the physical processes that you expect to happen. So on the bottom left here, this is an animation that was actually created only 1 or 2 days after the kickoff. So we've only got 6 weeks to build the robot. Everything's got to go fast. This animation was created in what we call PowerPoint CAD, where basically you can draw big colored blocks and move them around in PowerPoint, and you can draw them to scale exactly as they would fit into a robot. So creating animations like that is a great way to communicate ideas. Over on the right is a separate concept that was also generated really early in the season, where this is a 2D sketch in CAD. Showing how a separate concept where we would have had like a slanted elevator would have worked for climbing the 3 rungs you had to climb in the FRC game Rapid React. So the next step, as the others talked about, is the prototyping process. In building a climber, one of the most difficult things pretty much every year is figuring out a way to acquire and release the rungs or bar or whatever it is that you have to grab onto in order to lift yourself up. So on the left here is a video of a mechanism for latching onto the rungs passively and then using a pneumatic actuator to fire and release these claws to move on to the next rung. So this was a unique challenge in that you had to release a rung and then grab onto another rung in order to climb from like this level 1 up to level 2, 3, all the way up to the top rung. And over on the right side, you see a separate concept, which was developed to accomplish the same goal, but in a separate way. So it had like this sector gear thing that would latch onto the rung, and then a pneumatic would fire, which would drive a gear and rotate this around to release. We didn't end up going with that concept beyond this prototype because we found that the tolerances required were just a little bit too tight. When FIRST gives us games, they tend to also give us drawings of the field, which have tolerances on them. And the tolerance, like the allowable range that the center distance between the rungs could be, was so wide that having a claw that grabbed really tightly around the rungs was not going to work. So that's why we ended up going towards the left concept that you see. So once we've got relative confidence that our mechanisms are going to work and that we understand the physics involved in the problem, we hop into CAD. So on the left here is kind of the crayon CAD, as the others talked about, just showing where things will fit in. For this climber, we found that we had to stow it in this really unique way and deploy it up with a rotary joint. The crayon CAD is really for staking out the space that a mechanism is going to take up. And then as we moved into like the center image here, we staked out exactly how we would implement these things. So this shows where the sheet metal is, how big the sheets are, where the bends are. We like to do sheet metal because it allows for really, really robust mechanisms and pretty quick iteration with the sponsor that we have, who's able to bend those on a CNC brake. But at that stage of the process, we don't integrate like lightning pockets or put every single bolt hole that we need. And when we get into the third image is when we really get into the brass tacks and the details. We put lightning pockets to make sure that the robot will actually fit within the 125-pound weight limit that we have. We figure out exactly what the parts are going to be and get them completely prepped for manufacture so that we can eventually export 2D line drawings for these parts to be cut on a water jet and then generate bend drawings for the operator of the CNC brake. So one of the really cool mechanisms that we had on our climber in 2022 is what's called an over-center linkage. This is unique and cool in that it allows you to have very little input force. So you can see an air cylinder that only has about 20 pounds of force actuates a linkage, which rotates this claw around to close it and open it. And that 20 pounds of force based on this geometry actually translates to well over 150 pounds, such that we can fire this really small actuator and it releases the entire load. So when the mechanism is fully loaded up and the robot's hanging from one of these hooks, there's a lot of load going through it, but it's all directed into a hard stop until this tiny actuator fires and opens that up. The next step in the process is to actually build the thing and test it. So on the left here, you can see the mechanism working as intended on the gold robot. You see it swings up and around, shifts its center of gravity a little bit, and then swings up to the top one and then releases. It was a pretty violent transition between the rungs there, swinging around this big 150-pound robot. It's a lot of energy involved. On the right side here, you see the silver mechanism. So this, as the others talked about, goes on the silver robot. So this was built long before the gold robot, where we are able to figure out the problems. And here it is on a scale. So it's really important that we weigh our mechanisms to make sure that we don't end up over the 125-pound limit. But not everything is perfect. When we built it and tested it, in the bottom left here, this is one of the first tests that we did on the silver robot. Our mechanisms don't work immediately. You know, engineering is an iterative process. You can see we were going super duper slow here, climbing up. Second latch is on, and then when we released the bottom one, that mechanism worked great. But we found that the rung would actually slip out of the hook, and the robot would fall and smash into the ground. So we had to iterate a little bit on the geometry of the hooks in order to stop that issue from happening. In this top image here, you see that's a picture of the gearbox after only a couple of climbs. That gear right in the center of that image is actually a tiny aluminum gear that all of the teeth were stripped out after just a couple of climbs. So we found that we needed to upgrade that gear to steel and then didn't have that issue anymore. And in the bottom right, this is another failure that the climb had early on, where the lightning pocket was a little bit too aggressive and this rib actually broke under the enormous chain tension. So we had to redesign that part to not break and actually take the load that we expected it to see. And once we have a mechanism that tends to work, we're able to go to competition and make small iterations throughout the season. So we compete at 4 to 6 tournaments a year for the most part. And on this left image, you can see is actually a failed climb at the Irving district event where we went up, we were able to latch onto the rungs properly, but we weren't able to release. We found that the rung would wedge itself into this gap, and we had to iterate on the geometry a little bit. So in the right image, you can see some of the different hooks and latch geometries that we ended up going through. We kind of started with the gold one, moved into the white ones, and then eventually ended up at the red ones as our final design, which decreased that gap so that the rung wouldn't slip out and decrease the gap down below so the rung wouldn't wedge in weird places. And this iteration process is really just to very slightly increase speed and increase reliability so that we don't have failed climbs. So the 118 is a pretty old team. We've been competing in this for a long time. In 2016, there was a climbing challenge where you had to reach up, grab a rung, and lift your robot up. And we had this really novel grappling hook design where we actually fired a hook which would ballistically travel up to the rung and then hit it and latch around it. And then we would basically be attached to the rung by a string, and we would winch the robot up by that string. In 2017, we had to lift our robot up with a strap. So what we did is we dropped that strap and laid it on the ground and then sucked it up into a spool, which was powered passively off of the drivetrain. So when the robot drove in reverse, there would be a rotating spool with Velcro on it, which would suck up a piece of Velcro on that ratchet strap and then tilt the whole robot up and climb up to achieve those points. One of the most complicated and impressive climbers that our team has ever built was actually in 2018, where we deployed these hooks in the bottom left from a stationary point on the base up to this mobile part of the elevator. We would raise those up, and kind of like 2016, we would then latch onto the rung and have these strings, which pulled from kind of the front of the robot, as you see in this top image. So that would pull from as close to the CG between the two robots as possible. That game was unique in that you achieved a lot of extra points if you were able to lift your partner robot up as well with you. So we would deploy these forks that a partner would drive onto and then winch up both our robot and their robot from this string that kind of came from the front of our robot. And when we weren't lifting a partner, as we did in some matches, the robot actually went up in this really, really wacky, like tilting geometry. This was one of the most complicated climbers our team has ever built, but somehow we were able to make it work in probably about 75% of our matches. There were still some failures in that mechanism. And one of the most elegantly packaged climbers that we have had in recent years was in 2020. So you can't really push a rope. Ropes are meant to only work in tension, but we use that concept where we use these thin steel strips, actually from fish tape, which is used by like plumbers and electricians for running wires through walls. And so we would drive this spool with this thin strip of steel and actually push it up through this like 5-stage linear elevator. So we would push that up to deploy these hooks up to a rung that we would lift by, and then just reverse the gearbox and lift ourselves to the tension in that steel strip. This was one of the cooler mechanisms that we built, but it took a little bit of new engineering that we had not done before. And with that, I will hand it back. Oh, yep. So there are, the first gives us pretty similar challenges most years with how to, with what the robot needs to do in terms of climbing. Some of the lessons that we've learned in previous years, basically selecting a gear ratio for a climber is the same every year. You need to determine the torque that you need based on like the weight of your robot and the radius of an arm. So that's the load and the distance, which you multiply together to get your torque. And then you want to look at what motor you're going to use and try to determine the ratio based on about 1/3 of the rated stall torque of a motor. When your robot's climbing, you really need to worry about where the center of gravity is going to be. It's easy to build a climber that swings too much or flips the robot over, and you really don't want that happening when you're climbing. And you want to iterate towards a rock solid latch for how you're going to grab onto the bar or the rope or whatever it is that you're going to climb by. So on the right here is actually where our robot failed in 2017. It flipped on its head, smashed everything at a tournament, and ended one of our longest win streaks in our team history. So that was that moment of failure has kind of stuck with us, and we've built off of that and I think improved in recent years. And with that, I'll hand it back to the others, and I think we're going to do some questions soon.
All right, thank you, Team TechnicBots 8565 and Mustang Robotics 2313 for hosting us today. And we'll open it up for Q&A now. If you have any additional questions after today, you can visit us at our virtual pit on the first Saturday of every month. It's advertised on our Instagram usually, and the Discord link is, well, it's a tiny URL, it's tinyurl.com/118virtualpit. And our Horizon reveal video that's been playing in Jackie's background is on our YouTube channel, and you can visit us also at our website. Are there any questions?
Can you elaborate?
Okay, Dave, I think we're a little short on time, but if any other participant that may have any questions, they're going to be putting it in chat, and you guys can answer it through chat for a bit, and then we'll be moving on to our next session.
Okay, cool.
Thank you so much for your presentation. It was awesome.
Thank you.
Thanks for having us.
Huh? Oh. And now we will have Team USA, which is us, and Team Romania presenting the FGC field design. The team from Romania, also known as Team 19121, T-Borgs, an FTC championship in Houston in 2022. As the past representatives of their country, and they had great results. And then now they have lots of pressure to perform just as well, if not better. So Team Romania, are y'all here?
Oh, yeah.
Okay, so first we'll have Team USA explaining how what their build process was. So whoever has that document pulled up right now, who's sharing their screen? Can you like go full screen and then have the builders go through the slides to have a discussion? Max, can you share your screen?
Okay, wait. I think, are we lagging or are you lagging? We're not sure.
Am I lagging?
Not anymore. Okay.
Okay.
No, it's fine, right?
I think there's echo.
Is that echo?
There
There
is
shouldn't be.
there is an echo, it's fine.
Wait, are you? All right, yeah, let's just go. Okay. Camera on. All right, they can't see us. All right.
Hello, we're Team USA, and we're gonna explain how we built the field. So I'm Joseph,
I'm Mac. And I'm Andrew.
and first we started off with like measuring when we built the FGC field. So Max, if you want to explain.
At the top. Then it's like, oh.
Or just go.
Okay, so we first started off by taking the CAD file from the FGC website, where they actually have their own, or they have the step file of the field, which we then downloaded and then imported it into Fusion 360. And once we imported it, we were able to take all the measurements that we needed. So for example, wait, what'd you pause? Okay, so for example, we could take the measurements of the angle of each board and the length and the height to accurately get all the measurements and then put it on a piece of paper. So then it's easier for us to actually just buy the materials. For the boards, we actually bought wood and had them cut at one of our houses, and just putting it on paper made it super easy to see all the angles and all the orthographic views in order to get accurate cuts.
So next I'm going to talk about the build process. So first we needed to like buy all the parts, and we wanted a field that was one reliable, so like one that doesn't like shake and stuff and simulates things that we would actually see in Geneva, such as like the bouncing. So we use like polycarbonate for the top and wood for the bottom. And we also wanted to like focus towards like a more cheaper option. So we went to Home Depot and we got a sponsorship for basically most of the parts required to build the field. And then our main thought idea was like splitting it into different subcomponents so we could assemble it somewhere else. And we also needed to like cut all the different wood we got. So using different saws like coping saws, jigsaws, circular saws, miter saws, table saws, hand drills, and like sanders, we're able to accurately represent like the field in real life and bring all the cut wood and assemble it together into a good looking field. And so these are like pictures of like during our assembly, and the left picture is us drilling holes into the polycarbonate sheets so we can use zip ties to assemble it together. And on the right picture, it's like the frame for the middle. We also wanted like a very strong frame so it won't shake around, and a very good like bottom like foundation and supports. So we cut a lot of beams and put like wood plating over it so it would accurately like represent what we would see in Geneva.
And so here are the final steps in like reloading these parts. So if you've seen this photo, previously we built the field inside of a garage.
So previously, we built this field in a garage, but now it's transported to a new location. So the main way that we do this is by making sure all the parts are built lightweight, easy to mount and dismount, but also sturdy at the same time. So to do this, our strategy is to use nail gun and screws. So screws and nail guns are really easy to dismount, but they're also incredibly sturdy when given enough force. We also build a lot of subcomponents, just cutting the wood off, the hangers and everything. So it can be much easier to mount as well as packed together in a tight space. And that also ties into easy to disassemble and reassemble. Just don't make too many subcomponents. Just make enough where everything can be put together quickly and reliably. Finally, strong build with strong parents and support, which are easy to dismount, plus being lightweight, so transportation is more desirable. So that's pretty much our entire strategy here. And do you have any questions on our FGC build?
Okay. So let's see. So we have other teams here from the FTC Challenge, like Team USA and Team Romania. So Team Romania, do you guys have any like similar building experiences as to our field? Because I know on social media, we've seen lots of different variations of the FGC field, and we're just curious to see if you have any insight on your own field.
Yes, so basically we just put a lot of OSB plates on some spread out benches. We took some measurements from the unship from the project, you know, from the, yeah. And for the actual tower, we welded some, what do you call them? Some steel plates actually, and created the tower. And the hoop of the tower is made out of polycarbonate. And yeah, that's kind of how we did it. Yeah, everything else is just made out of OSB, even the fence. Yeah, that's kind of all of it.
But do you guys have like a field map from the FTC? Do you know like what material we're driving on?
No, it's a surprise for us too. Yeah.
Okay. Also, we were wondering, so you know, in FGC where like the field is like elevated off the ground, do you know how high it is off the ground?
I think it's 60 centimeters.
60.
I don't know how much it's in inches, but
Okay. Is there another team here from the FGC Challenge? I think.
Yeah, it's just Team USA and Team Romania today. Team Turkmenistan couldn't make it.
Okay. Okay, so I guess we can do.
Maybe you can move on to like tape.
So we have a quick question if tape is allowed to be used in FGC because it is not included in the kit, but we still have a question for it.
So is tape legal? Do you guys know if Team Romania, do you guys know if tape is legal in this challenge?
actually we've used tape for the top of the hoop, you know, because yeah. Oh, you mean with the robot?
Yeah.
I don't think so. Just the materials that come in the kit,
Not.
nothing else. I mean, you can use some zip ties, but they have to be similar to what comes in the kit.
So for the hangers, so I know this. Oh yeah, I know this year's challenge is kind of weird. So where everything in the shooting form is like all cooperative, and the only difference in between winning your match and losing your match is hanging. So like, you guys want to talk about your opinions on that? Because I feel like right now, like the shooting has like no purpose, serves no purpose in winning your match.
Yeah, so basically you can leech off of other players and just hang at the, you know, at the final match, at the end of the match, and yeah, that's about it. You can just be a leech and just win if you hang on the highest ledge. But there's the competition bonus. Yeah, that's something. You can get 1 point basically from filling it 60% of the way. Yeah, that's about it.
I think also, I don't know if you've tried, but we've tried shooting the balls into the hub ourselves. And it seems like fairly easy to get the ball into the center hub. So like we were thinking about like, is it really worth it making a robot that can shoot, or is it faster to do a human shooting than a robot shooting?
Yeah, basically we're primarily focusing on the human part. Uh, yeah, we decided that the robot shooting itself is not really that worth it. We're more focused on hanging the robot as high as we can. Uh, yeah. So that's about it.
Yeah, we were curious because like we were also considering a similar strategy, but if at that point I feel like the competition would turn into like a bunch of robots just waiting to hang at the end game and just people shooting instead of robots shooting. So it'd be kind of funny to see how like everyone approaches the game and see if we can play the game. I don't know.
Yeah, that would be really something.
Oh, so for the balls, I know the kit only has 6 balls. Do you guys have any other ideas of like where we can get similar balls, or like maybe 3D print your own balls for
Yeah,
testing?
we 3D print our own balls.
Okay.
Yeah, like around 100 we've 3D printed, but they break really easily. Yeah, that's about it.
Do you think about like rev parts? I guess like the quality or like overall usage.
Like, do you think it's easy to use? Do you prefer to use it like over other companies?
I'm sorry, I didn't get that.
So like the Rev kit, right? All the parts are just Rev Robotics. Do you like use like what do you think about it? Like each of the parts?
Yeah, it's our first time working with the Rev kit. Actually, we went with GoBuilda for the most part. Yeah, it seems it's okay. It's not that great actually. Like all the screws have to be placed before you have to plan out like the screws and where to put things. Yeah, just plan out the entire robot before building it. It's kind of a hassle actually. Yeah.
Yeah, in our building experience, like we take apart a robot a lot to slide in those hex cap screws in the extrusions. So
That's why we use T-screws.
that's why we find really annoying about the kit too.
The screws break really easily.
Also, building with Rev, it seems like your structure is not very strong because you have like plastic brackets, right? So I don't know about your
Yeah.
chassis. Your chassis feels like flimsy, where you can like kind of bend it because of the plastic brackets holding it together.
Yeah, our robot because of those parts, our robot real is kind of flimsy actually, but we try to use the metal joints actually. Yeah, and that makes it way more sturdy.
Hey, disconnected.
But should we ask about their chat?
I mean, they feel comfortable talking about it. It's kind of like competition. Yeah.
I know it's like, I know it's like, I know it's kind of like a secret still, but like, do you mind telling us a little bit about like your robot, like what type of chassis you're using, or like how your shooter hangar looks like?
Yeah, so basically our shooter is the human player.
Okay. Okay.
Yeah.
Okay.
So
Okay.
yeah, we
Yeah, we're
have
also
two-wheel drive on the back and two omnis on front for direction. And that's about it.
yeah, so yeah, similarly, like right now we have a like a robot shooter, but we also consider like a human shooter because obviously I feel like it's a lot faster. Yeah, for a chassis, yeah, we went with the 6-wheel drive chassis with like the two wheels and the two motors in the center being lowered. So it's like a standard FRC chassis kit given by AndyMark. It works pretty well for us. You can turn pretty quickly, but also going off the human player shooting thing. Do you guys know any specific rules for the human player? Like maybe you can only hold one ball at once, or like there's a limit to how fast you can shoot. Like, are there any limitations on the human player shooting? Because I feel like it's kind of unbalanced if like human players can just toss the balls in so easily. I know the robot video is different.
Yeah, I think it's two at max he can hold, and there's no limitation on how fast he can grab and throw them basically. So yeah, as fast as the human player can, I guess.
Do you have any questions for us? Like, we've been asking you the entire time. I think it's, it's like interrogating right now. But yeah, you like ask us a question.
I don't know. Maybe my colleagues can have some questions, but yeah, I think you've told us basically like you've given us an idea about your robot, and I hope we did the same.
Yeah. Okay. Okay. Well, I think that's it for our session. It was kind of cut short, but we're also running behind. So we'll be eager to see you guys in Switzerland when we compete together. And like, we hope we can do well at the competition.
Yeah, same for us. We hope we'll have some matches together actually. Yeah, it will be fun.
Thank you so much for your presentations. So now we have one last drawing before we end off the session. So let me just share my screen real quick. And just a reminder, if you do win the drawing, please DM me on Zoom with your contact information, including your email, please. And now we'll do the drawing. Oh. Hi, I might pronounce this wrong, but Cancel Pep, you have won the $50 Rev gift card.
Woo!
If it's possible, can you please DM me on Zoom before you leave? She's still here?
It's really depressing.
Oh, looks like she left. So we'll just do another round of drawing then. All right. Daria, are you on the Zoom session? So please send me your information. I just emailed you, or I private messaged you on Zoom. If you could please respond to the question and give me your email, then I'll have the Rev gift card forwarded to you after the workshop. Okay, thank you so much everyone for joining the session, and I think we will be ending our first global challenge track here. And thank you so much, and have a good morning or night.